today I'll be presenting Nescience. It's a way to bridge the gap between privacy and efficiency. And to start with this first, I would like to give a small quote about what Nescience is by a British poet. So I quote, "There is nothing so minute and inconsiderable that I would not rather know it than know it." So this is actually the definition of Nescience, which means in our days, lack of knowledge. So, what does Nescience mean to us? Actually, Nescience is a privacy-centric zkVM designed for both private transactions and public transactions. It will be offering a user experience like public blockchains, but with additional privacy features. We are trying to find a proof system for private state updates, and this is to ensure minimal trust assumptions and to prevent information leakage. We would like the proof verification and public function executions to be delegated to external provers. And the zkVM actually would facilitate an interplay between public and private states. So the goal towards Nescience, we have different goals, so we are still exploring. So we would like to create a state separation architecture. We would like to create a virtual machine, to implement proof creations and verifications, to adopt a kernel-based architecture implementations, and to have some interaction design. So before I continue, when I was preparing to this talk, I was thinking, what should I say? How should I present the work? So actually, the work is still work in progress. So this talk will be more like an exploration on what we should see, what we should look at, what we should consider when building a zkVM. So it's to encourage the community, researchers, developers to be part of it, to contribute, and to understand what are the main issues when we want to build a privacy-first zkVM. So the idea behind state separation is to design a unique architecture that can differentiate between public and private computations. We will have an account-based model for public state and the UTXO model for private states. Well, actually, the UTXO model creates new UTXOs for subsequent transactions, and the account-based model actually allocates balances to accounts that can be altered by transactions. So if you can see here, sorry. So if you can see here, it's not working. Fine. So the account-based model actually, in the account-based model, every participant have an account, and then transactions are directly modified, modify the balances of these accounts. And in the UTXO model, it treats every transaction as a new input, and the output can be used as an input for future transactions. So what are the state separation benefits? We have, in this table, we have different things to look at. So we can begin with the privacy and confidentiality. Actually, in a single state, data is housed together, even if it's encrypted, meaning that an attacker can have a pattern, can build a pattern and understand something. While, well, I call it Nescience benefit, but it can be seen as state separation benefit. Private transaction actually can be obscured. Regarding the flexibility of operations, in a single state, actually, there is no catering to diverse needs. So sometimes we have speed, some transactions or some operations need to be faster, need to be more complex or simpler. With the state separation, simple public operations can proceed while complex one can be executed in private. We also need to look on scalability, where in a single state system can be clocked, while in a state separation, heavy private operations actually don't hinder the performance of public ones. Regarding the security protocols, actually in a single state, we will have a single security protocol, which may be too relaxed for private data, but it may overkill the public data. When we adopt state separation, actually, what we will have is a tailored security protocol for private transactions and a more relaxed one for the public state. And finally, we would like to look at composability. So in a single state, interaction would require a lot of checks, while in state separation, public function can reference to public functions, and private functions could reference to private ones. So now that we have the benefit, we would say, oh, OK, let's do it. It's fine. Well, to do that, we need to find a way to harmonize between these two systems. So here is an exploration of 5 things that we can consider in order to be able to harmonize these two systems. So we can think about a translation layer that has the role to have an interface between the UTXO model and the account-based model. And this can be done by having an adapter, a UTXO to account adapter, or an account to UTXO adapter. And we are still looking at this to understand how we can do it, how we can translate some UTXOs to account-based, and then what we can do is to have some layer to mirror the UTXO executions. And regarding an account to UTXO adapter, what we can do is when someone wants to send a private transaction, he can just convert some of its balance into UTXO and then send private transactions. We would also like to look at a unified identity for both states. And this can be done through deterministic wallets, meaning that we can generate, a user can generate multiple addresses for both private states and public states using one seed. We would also like to have, of course, cryptographic commitments to commit to the state of both models. This can be done through Virtual trees and KZG because Virtual trees are small in size, so transactions and verification could be fast, or by adopting the Mimble-Wimble style aggregation for UTXO by aggregating different UTXO accounts together. When we do this, and when we can get to this point, then we should think about batching process and some anonymity sets. And this has the role to have several UTXO private transactions into one single public account-based transaction. And this can be done through, there are a lot of techniques that we are looking at, but some techniques could be the coin join technique or the tornado cash principle. And last, what we are looking at is to have an event-driven system where some actions in a model would execute depending on events in another model. This can be done through conditional execution where a smart contract is set to be executed depending on the UTXO model. So a smart contract can, for example, release some funds on an account-based model only when a UTXO is spent. So these are the ways that we can harmonize these two systems together. And till here, it's fine. You would say also, wow, OK, it's fine, we'll do it. But to do that, actually, there are a lot of challenges, and there might be a lot of solutions. Here are some of the challenges and possible solutions to those challenges. So when we combine or when we want to merge two different models, we will have some synchronization challenges. Possible solution can be done through state channels, meaning that transaction could be executed off-chain and then only the final output can be on-chain, or through side channels, side chains where everything is done side chain and then there is a synchronization with the blockchain. Otherwise, with having some checkpointing to verify the harmony between the two systems. Another thing we should care about is double spending. So there is a risk to be double spending on these two models. One way to solve this could be by having multiple signatures, meaning that on the both models, meaning that transactions should be signed by both models to avoid double spending or to avoid unauthorized transactions. It can be done through cross-verification mechanisms, or it can be done by timestamping in smart contracts, where then we can order them sequentially and see where there is a double spending. Regarding the security, actually, of course, if we are merging two different systems, there would be some vulnerabilities. These vulnerabilities can be tracked through a threat model to prevent some attacks, or by layered security using the fail-safe system to prevent and make sure that some failing in some transaction wouldn't endanger the whole system, or by adopting some decentralized watchovers that will look at transactions and verify which transactions are not behaving or are misbehaving. And finally, of course, we need to manage the gas and fees. And since this dual model can lead to fee structure like a high fee structure, so this we are still looking at, and a possible solution could be dynamic fees adjustments, some fee estimation tools, or unified gas stations where a user can allocate gas for both transactions at the same time in both models. So now that we have seen this, we would like to focus a little bit more on our zkVM. So what we would like to do is to find a high-performing environment to compute and execute transactions, putting always into consideration that we need to look at some privacy features and have some privacy considerations. So WASM and RISC-V are adaptable to UTXO model and the account-based model. WASM actually operates as a low-level virtual machine capable to execute code compiled from various high-level languages. RISC-V has the potential to enhance security and privacy within trusted execution environments, but they are not optimized for zero-knowledge proof applications. And lately, we have been thinking about what proof system can we use. So we were looking at Nova. So actually, Nova enables efficient executions using IVC and folding schemes. Folding schemes actually permit the approval to integrate proofs from previous instances into R1CS instances. It supports parallelization, no need to FFTs. So there is an improvement of proof generation speed, and it has a very low memory consumption. So to do that, actually you can see our repo. Oh, sorry. You can see our repo here. What we are doing now, we are trying to do a fair comparison, actually. There are a lot of benchmarks that have been done with Nova and Halo 2. But none of them are considering the, let's say, like the recursive hash functions. So what we are trying to do now is we are implementing Nova, Halo 2, Plonky, and Starkey by modifying the code and by implementing Poseidon 2 in order to understand and to justify to ourselves if Nova is actually efficient enough for our proof generation and verification. It's a work in progress. I think we have made most of them. We are still just having some issues with Halo 2. Our repo is public, so if anyone wants to have a look and maybe just contribute in it, it would be great. And yeah, so then I will just talk a little bit about what we want to achieve with proof creations and verifications. So actually, we want the user to be able actually to generate its own proofs. The verification actually and the execution of public function will be assigned to external prover, and this is because we want to prevent data exposure. I think that we should implement a reward system, and this is to motivate provers to verify. the verification cost actually should be less than the execution cost. And then we would like to combine proof of stake and reputation systems and do some regular rotations. And this is because we need to ensure that the system is secure and reliable. So yeah, what's next? So actually, we are thinking of implementing some mechanism for proof creation and verification. We would like to empower the users to generate their proofs on the private state updates. We are investigating decentralized verification processes with multiple external provers and how to make them, like, for example, verify each other's work. We would like to introduce a dynamic reward system for performances. And we would like to strengthen our system security against potential adversarial actions. This is our website, and this is my contact on Telegram or Twitter. So please feel free to contact us. This is just a way to give some exploration work about what are the things that we need to consider when we are creating a zkVM, a privacy-first zkVM. So yeah, that's all. Thank you. Any questions?
I have a question, actually.
OK. Thank you.
So you're exploring VMs and you want to generate them proofs client-side. You're wanting to generate these proofs on the client side, like on a user's device. Is it going? Can a VM work on a user's device? Are you like exploring it working in mobile phones or? Okay,
actually. Well, actually, I know that it's difficult for that to happen on a VM, but since the project is still new, we are still exploring. We think that it's difficult, but I think that it's worth the time to search for some solutions. And like, even if it doesn't work, actually, what we are doing is trying to understand the challenges that might come from that and how to find a way to find a solution, or maybe not find a complete solution, but maybe start to put this in public so people can get interested in, the community can contribute, researchers can, go through that path maybe and find some solutions. We still don't know because we are still exploring. Maybe we will be able to. I know it's difficult, I know it's hard, but yeah, that's why we are here.